our session first. Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. Okay, yeah. Today we will have session with Dr. Gulam Mubashar Hasan. He is with Department of Computer Science and Software Engineering, University of Western Australia. He will present about deformation measurements in the presence of discontinuities by using intelligent algorithms. Okay, we will have separate question and answer session after the presentation from Dr. Gulams. But if you have any question, you can also feel free to drop in the chat rooms. Okay. Okay, I think that's all from me as a moderator for today. If uh, Professor Mubasar already, if you are already prepared for this presentation, yeah, the time is yours.
Okay, thank you very much. Thanks a lot, Munif. Welcome everyone, and Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh, everyone. It's a good day to actually Friday to have the presentation, and it's maybe a good morning for your guys, and must be a good weather. So my name is Mubashir. I'm working in Department of Computer Science and Software Engineering in the University of Western Australia. Some of you may know or not that Ari Shidiki was the one who used to sit with me. So so thanks a lot for inviting me for the talk. So today my talk is basically deformation measurement in the presence of discontinuities. That is the problem. And I'm using intelligent algorithms to actually solve this problem. My research interests are artificial intelligence, machine learning, image processing, and their applications in the multidisciplinary problems. So today my talk will be discussing about, first of all, I've just taken one single problem, and that is actually my PhD problem, and then from there how I led it into the more fields. The importance of their problem, what are the challenges, what are the solutions, results, some future work, and the feedback, or like actually question answer sessions if you have got any. Deformation measurement. So we normally in our life, we have seen that many things change over time, and same is the case for the transformation of bodies, like human bodies change. On top of that, the earth, all those things, they change. Now, how are the deformations? So you can see this is the one of the ground deformation on the Mount St. Helens. What happened is that you can see that actually over the time, you can see the earth is shifting. Now, this becomes a very interesting case because can we measure the deformations, how it is changing? And if we can find out those changes, then we can predict actually what will be going to happen, or we can analyze what to be done to avoid it in some scenarios. This is mainly the problem came up from the engineering, and engineering, it is known as the reconstruction of displacement and strain fields. Now, what happened? What does this mean? This means that if you have let's suppose this wire, you can see this yellow line. Can you find for each and every point of this yellow line where it has been moved in the other image or after the deformation where it is? And that actually makes the entire field, that how the entire field has been made or entire line has been moved in both horizontal and vertical. And that is known as the displacement field. Similarly, if you take the derivatives of them, that will be called as the strain fields. Now, this is more in the engineering terms, but now this is a good image for you guys to actually understand the problem. Many of the times, like actually, as you may know, that Western Australia is the mining focused country, and there are many, many mines here. So what happens is that if we keep track of the health of the mines, and if we keep track of the walls of the mines, what happens is that we can evacuate the labs on time before any catastrophe happens. Because remember, every year we lose few lives in Australia, which is a developed country. We lose some lives in Australia because of those collapses or something like that. What happened is that it really costs a lot because companies have to pay a lot of insurances and all of that. Those lives, we can never get them back. So that's an expensive loss. Excuse me. So that's why structural health stability, it is not restricted to mines. It can be done on the bridges, it can be done on the buildings. And I hope you guys know about like what happened in the Bangladesh, like I think so 8 or 10 years ago, like in the 5 minutes, just 7-story building collapsed and more than 1,000 people died. Similarly, we can measure the strain in the materials, like or the deformation in the materials. Then when they are under the load, we can also look into the electrical engineering where ICs, and when ICs are performing, they actually heat up and then there is a thermal expansion. On top of that, biomechanics, it is again the body parts which we create in the biomechanics. We found that actually how they will behave under the pressure. Load testing of aircraft, when the aircrafts are under the load, especially with the winds and all those things, how there will be a deformation acting on them. Vibrations, yes, earthquakes are very, very important, and earthquakes, normally vibrations can be measured at how much vibrations happen. Now, on top of that, these are, if you look into it, these are most of them engineering. The medical sciences is also, because the tumor growth is a very, very difficult and challenging problem. What happens is that, let's suppose you have a tumor in your body, you have to find it out that how it is changing. And you need to really know very, very high accuracy with it. Similarly, when we actually open up, or the surgeons open up the human body, what happens is that the tissues deform to react, because as soon as you actually incise it, you make the incision, the tissues around it deform, they change their shape. And it is very important to know how the tissues have changed. Otherwise, we can actually cut the wrong parts. Then obviously, for the laser treatments in the medical systems or hospitals, we need to know the equipment stability positions, that they are not, because what happens is that, let's suppose you have got the MRI equipment, there are a lot of vibrations in it. So after the testing has been done, we need to ensure that actually they are stable and they are not moving. Otherwise, we may be actually targeting the wrong body parts or wrong areas. So now, what are the regular techniques? In engineering, most of the time, or some other place, most of the places, till the time of, you can say, 1990s, we were using strain gauges. So there are different type of strain gauges. Like first they were electrical, mechanical, then electrical, then electronics. With the revolution of electronics engineering, piezo resistor gauges. Now, all of them were actually, one of the things was that they were sensitive, like some strain gauges, normal electrical ones, they were sensitive to temperature, humidity, and also it was difficult to repeat the experiments. Electronics one, they were good in those days, but they were not, they were precise for a small strain, but they were really, really expensive. Again, the temperature changes a lot. Also, if they heat up, their performance will be affected. One of the major limitations of these strain gauges is basically they can measure the deformation of single point in single dimension. So if you go back and remember that line which I've told you, it will be just telling me that it is moving horizontal or vertical. It cannot tell me that actually both of them have been taken. Also, it will be just focusing on one point. Around the sides, what is happening, or other points around that, you cannot actually find anything. Now, if you look at those of the experiments, it is nearly impossible to repeat the experiment. Like you do not want to have the earthquakes again and again to find it out that what is happening. So it is very, very difficult to repeat those experiments, even in the labs. And we cannot expect the same behavior. So then actually the revolution came up with the cameras. And from cameras, we got the images. And once we got the first, we had laser, and then actually we have got now the images. And those images can really help us to actually measure the deformation. And we do not have to be in contact with the surface. Otherwise, strain gauges are normally contacted to the surface. Now we do not need to, because we can actually remotely measure that what is the deformation. And that really revolutionized the field of the deformation measurement. So what is the idea of the digital image correlation? It is very simple. You can see, if you can see my cursor, if you cannot, just let me know. You have a point and you can see this is an image or a part of an image, and I want to locate where it has been moved. And now you can see there's a deformation. This point has moved, but actually the area surrounding it has also been moved. So what I do is that, this is the statistical correlation technique. What I do is that I try to match the patterns, and I try to maximize where the correlation is the maximum. So correlation is the normal statistical technique, like you try to match two different patterns, and it is like used in the stock exchanges and all those things. But in those cases, they are normally two-dimensional. Now, one-dimensional. And now we have got two-dimensional, like we have an image which has X and Y. So we try to actually maximize the correlation, and that's why we know as a digital image correlation. Wherever we get the maximum point, it means this is the new point which we have got. Now, what is the range of correlation? It will be either -1, like it is opposite, or 1. 1 means maximum correlation. So once we get the correlation, this is the equation. You don't need to understand it a lot, or the point is that it is the correlation. One of the things what we do is that we have the, you can see this one, we try to move it, and we try to move such that actually we try to maximize or optimize the position, new position of U and V. So as soon as we get the new positions of horizontal and vertical displacement, we get the maximum correlation. And in this equation, you can see this U and V are the ones which are the horizontal and vertical movements, and they need to optimize. So when we get the maximum correlation for any values of U and V, we call that as the new point, or that is the deformation which has happened in the point which we are looking for. As I mentioned to you, correlation values ranges from -1 to 1. Yes, we try our best to reach the 1, but it rarely happens that we reach. It is like 0.99 or something like that. It happens. Now, giving you an example, imagine this is a Linus image, very popular in computer vision. We have actually this image. What I do is that I move it, and you can see I'm trying to track the center of the eye, and you can see there is a black box around it. This center of the eye, now this image has been moved. I want to see that where it has been moved. So what I do is that I try different U and V values. And when I get U and V, U is equal to 10 and V is equal to 15, and then I correlate it, it will giving me the maximum match. And that means this is the new position. So you can see in simple words, for the digital image correlation, we need to optimize horizontal displacement and vertical displacement. But in this case, you can see the square remains the square. It doesn't change. But in normal life, what happens is that our square becomes trapezoid, or even it has curved sides. And we have to figure it out how to. So for those things, what happens is that we do not have to optimize or estimate the new position of U and V, but we also have to optimize their partial derivatives. And once we optimize them, that these 6 optimizing variables, we need to optimize them to get the maximum correlation. Now, there are many challenges in this research. Number one, as a computer scientist, we cannot rely on lab experiments, because lab experiments take a lot of time, first of all, and secondly, we do not know the ground reality, ground truth, what is it? So conducting lab experiments is and especially we cannot repeat the experiments. So it is very challenging. This is the first challenge which we had to look into it. Then how much area around the image around the point should be taken? Because remember, if we take a big area around it, it will take a lot of processing time. If we take very small, then it will not have enough information to match it with a new position. So we need to have the optimal size. One of the major thing about digital image correlation is that we are looking for very high accuracy. And high accuracy means, like in terms of images, you know, the image points are known as pixels. We are looking for 1/100th of a pixel accuracy. We need to optimize 6 variables. And one of the major challenges that DIC, or digital image correlation, fails in the presence of discontinuities. As soon as there's a crack or there is an opening, something happens, it fails. How to overcome these challenges? That was part of the research. So the first thing which we did is that we created actually distress simulator. That is it stands for digital image synthesizer to reconstruct strains in solids. It was really, you can say, de-stressing us, because we got rid of the labs. What happened is that we created software which can actually look into this high accuracy, like deformations. We can just give the deformation equations. It will create the deformations images. It will generate one image before deformation, one image after deformation, right? So we call the image before deformation as reference, and the other one we call it as a deformed image. So we get both types of images. It is very time efficient. It helped us a lot. The only things which we have to provide other than deformation equations, how much. So can you see these dots? These dots are very important because these are the pattern which we are trying to match. They should be random. So it will be actually asking us that what are the speckle spacing. So these dots are basically circular, you can say circles, right? Filled circles, black circles. So we want to say how much should be the average spacing and what should be the size of each and every circle. So whatsoever, it gives us this speckle pattern images. One is the reference, one is the deformed, and then we can actually play with it. And we know what are the actually ground truth about it so that we can actually test it and we can match it with the ground reality. So this solved our first challenge. Then we came up with the second challenge. What should be the size of the image or subset size, which we are taking under consideration? How to actually optimize it? Now, again, it depends a lot on a pattern. So then what we did is that we came up with a new intensity variation ratio where we were looking at the div, like subset size, an image around part of the image around the point, and we try to see how much is the variation. This is the equation for that. The only thing which we were doing is that we were trying to increase the intensity ratio such that we get the maximum correlation, okay, or maximum DIC results. We tried many different values and we realized that actually the intensity ratio and our recommended one is 1.5. So 1.5 is the ratio if the image or the area of the image around our point which we want to find the deformation, if it has the intensity variation of 1.5, that is good enough for us to actually proceed with our DIC experiment. So what we did is that we created it as a dynamic one, like it will keep on changing, looking into the pattern, and it will adjust itself accordingly. After that, we took the challenge of this in red. What will happen if the failure happens? Because if there is a discontinuity, how will? Now, discontinuities, remember, it is a technical term. It means that the image has been split open or the crack appeared, right? So look at this image on the right, my right, like if you look at the pointer, you can see there is a wide gap which appeared, and that is the crack, or that is the discontinuity which we have got. Now, if it is continuous, if it is continuously same, we call it actually dislocation, like it has just opened up. And if it is a crack, it will be different crack openings. So the first thing which we did is that we extended the DIC algorithm and we combined it with the pattern matching. The pattern matching was very simple. The solution was actually pretty much easy for us because what happened is that, let's suppose this red area, you can see this is the area where discontinuities happened. And we figured it out that this is the area where our DIC failed. Once we get to know that our DIC has failed, what we do is that we use the pattern matching technique. Now, the pattern matching, if you look at this green with the reference of this yellow point and this yellow point, we try to find what are the two new positions. And these two new positions, either it can be on the right of the crack or on the left of the crack. As soon as we get to know right or left, what we do is that we took the small section of those patterns and try to match them. Whichever pattern is actually making a bigger match, we consider it that this is the new point. Okay. So you can see this is the original deformation which we had in the introduced deformation, you can call it. And this is the discontinuity which we had. You can see on the right top, this is what DIC result was. It is failing in this area. Can you see this white area? It was all failing. And then we reconstructed it here. So our algorithm with the extended DIC, it was able to measure. But you can see still it is not smooth, close to the discontinuities. This is the red region. Yes, results, again, it was successful. We cannot say that it was not successful. But if you look into it, we conducted different experiments with dislocation, fractures. Results were not amazingly. We are looking for a very high accuracy. As I mentioned to you, it was giving close to 1/10 of the pixel, but you can see the fracture case, it was not performing well. So we needed to bring something better, but again, this accuracy was better than the pixel accuracy. So what we did is that we created a new algorithm, that is, we changed the mathematical equations of the digital image correlations. And now I came up with the idea that we should have a discontinuous digital image correlation, that DDIC. What the procedure was that if this is the subset which I'm considering, and I always presume that it has been split from the middle. Now, obviously, it is very easy to manage that actually every time it is split in the middle. And let's suppose if it is not split, this split will be 0. Now, as soon as I consider this split, there are 3 factors to be considered. One, there will be horizontal split, vertical split, and then the angle of the split. These 3 things I needed it extra to optimize it. Now, let's suppose if there is no split or no discontinuity, then my bx and by will be 0, and automatically angle become unnecessary. But otherwise, there will be some distance b vector, and it will have horizontal and vertical components, which I need to find it out. And if I can maximize the correlation using optimizing these 3 values, then I will get the maximum correlation. In theory, it was very good. The problem is that we already have horizontal vertical displacements, gradients of displacements, and now we have got 3 extra variables, bx, by, horizontal, vertical, discontinuity gap, and its angle. Now, optimizing 9 variables, if you have experience, it is very challenging. It was pretty much all our optimization techniques failed. So what we did is that we did a 2-stage optimization method. So in the first stage, what we were trying to optimize was the DIC variables, 6 variables. And then in the next stage, we are trying to optimize these 3 variables. And that's how we were trying to maximize the correlation. Interestingly, I do not want to go to the mathematical detail, but interestingly, the results were really very good. If you look into it, we had a very good accuracies. You can see compared to the last DIC algorithm, we had a very good. We actually had the dislocations at 9 multiple angles, cracks at the multiple angles. We also conducted the results were the best and beating the state of the art of all the techniques. It was very highly accurate. The downside was that it was computationally very expensive. Now the question is that why it is expensive. If I go back to the slide, let's suppose if there is no, imagine if there is no discontinuity. What happened is that I am still trying to optimize these 6 variables, and on top of that, I'm trying to optimize these 3 variables. And that is actually taking much more time. So what I need to do, I'm wasting a lot of time, because if there is no discontinuity, my DIC can work well. I do not need actually to optimize these 3, but it takes really long time. So what we did is that learning from the pattern matching algorithm as well as DDIC, I came up with the intelligent algorithm to take the decision. So I created an algorithm which will be taking its decision, and it will be taking the decision by looking at the images, and it will see that actually which type of situation is there. Should I use DIC? Should I use DDIC, or should I use pattern matching? So all these things. One of the downsides of the DDIC was that the crack boundaries were not actually well identified. So what we did is that pattern matching, we tried to use it to find the boundary lines also well. So it is computationally not as efficient as the pattern matching only, but it was computationally less expensive than the DDIC. And we also saw that the results were actually getting better. So what we did is that one of the results were remained the same for DDIC, except that actually when there was a crack opening. So you can see this is the dislocation, and blue line is the introduced ground truth. So what we did is that if you look at the DDIC, this is all green points. And you can see some of the green points are here down, because this is the position where it could not find actually the crack line. and then look at this, our DPM algorithm. It was very intelligently, it was looking, it was always and always better than DDIC. Similarly, for fracture, our case was very, very good, because you can see this green is basically again DDIC, and it failed a lot. And especially when the crack is very, very small, it is just opening, it failed a lot. So what we did is that we have got DPM algorithm, which was working far better. Again, this is the area you can see when the crack, the tip of the crack, which is opening, DDIC even failed. But again, overall, it was the improvement as compared to the DDIC technique. Now, this is the research which happened. And then what we did is that we looked into it, at how it can be applied into the different fields. So what I did is that I actually looked into it. We got actually a grant, recently grant of smart roadside barriers with enhanced sustainability and impact resistance. This grant was in collaboration with the industrial partners of all the traffic departments in Australia and some of the industries. The idea was that actually we were using the roadside barriers, and we were trying to see that how the deformations happen in them. Now we'll come to you that what is the difference in these roadside barriers. The second one was with the Harvard University. I created a grant, and we are still working on it due to the COVID situations. We could not travel a lot, but we are trying to put up the National Institute of Health grant. The idea was that actually, when we have a neurosurgeries, like a brain surgeries, what happens is that the brain deforms as soon as you open up the skull. Also, when we take out the tumors, the brain deforms to fill up this wide gap. How it fills it up, and how much deformation it happens, and what is the rate of deformation, all these we need to actually look into it. So that's why this DIC and DDIC deformation measurements, they can really help us a lot. This is in collaboration with the Harvard Computational Radiology Laboratory. And again, it is still in progress. Both the projects are still in progress. Now I will talk about the first project. This is about the rubberized concrete roadside barriers. What is the rubberized concrete? Is basically, normally we have these cement barriers. So the car comes in, it hits the barrier, and what happened with the barrier is that all the impact has been pushed back onto the car. So what happened is that you can see in the second image, the car has been thrashed, right? Barriers, they may have the cracks, but normally barriers are very stiff, and they actually crack the cars. What happened is that most of the time it's the loss of the lives, because barriers are not happening. So this is the new rubberized material. What happened is that you mix the rubber in the cement during the manufacture process of the roadside barrier. Now what happened is that it can take the shock. So when the cars come and hit the barriers, what happens is that it takes up the shock. All the shock is not being, according to a Newton's third law of motion, is not actually pushed back to the car. It takes some of it. And one of the good things is that what happens is that it crushes down. It does not actually, just hit the car. If the impact is too much, it will just crush down, and it will expected to help to save the human lives. So in our projects, what we are trying to do is that and the idea is that where DIC will be used is that we have the drones, and they can go, and whenever there is actually an accident or not, the drones will keep on surveying the entire roadside barriers, and whenever it finds some deformation in it, it will report it. We can actually assess that deformation. Either it is because of the crack or not crack, but we will assess it, that what type of deformation is it? Is it a reasonable time to actually look into it and replace the barriers or not barriers? And also, when the crash test happens, we will also understand and try to look into it, that how the deformation happens when the car crash into it. So there will be real cars which we are going to crash into the rubberized concrete. So we are right now in the second phase of this project, and we are progressing well. That's all from my side. So if you guys have any questions, please.
Okay, thank you, Professor Mufazar, for your presentation. Okay, right now we will move to the question and answer session. Okay, for the participant or for the students that have question, you can raise your hand and I will allow you to ask your question. Or you also can write down your question in the chat room, and then I will read it. And or if you are uncomfortable with English, you can also write your question in Indonesian. I will try to translate it into English. Okay. Okay, Shaina Yandri. Yeah. Okay.
Yeah. Hi.
Hi,
Okay. Yeah. Hi, Professor. Thank you so much for your presentation. Yeah.
welcome.
Actually, yeah. I only wonder for your proposed algorithm, the DPM algorithm, right? The one that optimizes like giving decision, like the intelligent system, should you use the DIC or the pattern matching one? Yeah, I wonder like how are the rules to this to make that decision? Could you maybe give some a bit more explanation for that point? Because it's interesting to know that actually the result is way better and but the computationally is like actually less complex. That's my question. Thank you.
Yeah, that's a very good question. So to be honest, it was more an attraction for you guys to actually make you enthusiastic about this problem. So the question is very great, actually, to be honest, and it's very technically good question. Whenever it takes the algorithm works on it, that it looks at the pattern and it tries to figure it out that is there any discontinuity on it. Okay, as soon as it gets to know there is no discontinuity, it will go ahead and proceed with DIC. If it gets to know that actually, no, there is a discontinuity, then it will proceed with a DDIC. And if it realizes that actually DDIC is not giving a good results, then it will move on to the pattern matching. The question is that how it will make the decision. Now, the decision is all dependent on the correlation value. So when we correlate the two images, we try to see what are the correlation values. If the correlation value we have found that actually if it is above than 0.9, it means we can solve this problem using DDIC. If not, then what we do is that we try DDIC. So then what happens is that correlation value, we try to actually use DDIC to maximize it. If it is maximized, and again we get actually 0.9 or something higher, it means this problem has been solved. Otherwise, it means we are so close to the crack that actually we need to use the pattern matching. So technically, for each and every point, we are doing DIC for sure. But we are trying to avoid doing DDIC again and again because DDIC is very, very expensive, computationally very expensive. So that's why all our results, they were pretty much same as the DDIC. Why? Because at the end, we were doing DDIC or DIC. So DIC is already higher accuracy. This is the only thing where this pattern matching comes in is close to the crack boundaries or discontinuity boundaries. This is the only point where we were using pattern matching because it was giving us better results. And pattern matching, just to give you an idea, if you remember, it was the most, like it was far much actually faster than actually DDIC. I hope I answered your question. There is my research articles. You can also look into it. Which one is it? Extended digital image and discontinuous to reconstruct dislocation approach and digital. This one, so number 8 one is the discontinuous and pattern matching algorithm to reconstruct displacement and strain freeze under deformation. It is published in International Journal of Engineering Applications of AI. I hope I answered your question.
Yeah, thank you so much, Professor. I'll look into your paper and maybe read for more details. Thank you so much.
Yeah, sure. Yeah, sure. Welcome.
Okay, thank you, Shena, for your question. Okay, we can move on to the next participant who want to ask the question. Okay, you can also write down your question in the chat room, and you can also use Bahasa to write down your question. Feel free to ask your question. Okay. Okay, maybe if there are no question, I think I have some question for you, Professor.
Yeah, sure.
I think Okay, as I know that from your presentation that we only calculate about the deformation and also the cracking of the structure or maybe the earth. I think. Do you also have some maybe research about the do we have needs to have background in geology or civil engineering to understand this research?
Honestly speaking, no, not at all. Because when I started, my background is not at all from the civil engineering. So I had no idea what the civil engineering. And if one of this reason is that actually, if you remember in my challenges, when I got this problem, I was from the computer science background. I wanted to do my PhD in computer science. I never had civil engineering. I never liked geology or civil engineering a lot. So I thought actually what I will do with it. The major problem was there how to get the actually. So I got to know that actually I will be playing with the images, but the problem was that actually how I'll get the images. That was one of the major restriction when I started. So the first thing what I did is that I I looked into it. I tried to understand how to collect the data, and I got to know about the lab experiments. So the lab experiments was very tedious task. What happened is that what they have told me that okay, first of all, you have to actually order the material. The material will arrive. Then after material will be arrived, the next step is that actually you will frame it in a specific size. Then you have to book the testing rooms where the load can be stressed on it or deformation can be made. And then what you will do is that you have the camera in front of it, which is taking the images, you have the lighting, all these things. And then after that, whatever happens. So I realized like they told me that it takes about 2 months or 3 months to conduct one set of experiments. And it is not actually 100% that foolproof, that many of the time it fails and you have to go back and do it again and again and again. So when I started my research, it was one of the, I said, okay, I cannot do this thing because it is not possible. And especially I do not have the permission to enter the labs because I'm not civil engineer. So that's why this is the first challenge which I got. Conducting lab experiments to collect data. I never wanted to do it. It was difficult. And also it was challenging because you cannot repeat the experiments, and there were formation equation, and it will generate the images. And I have to play with the images only. I had nothing to do with the civil engineering. Yes, the application is in civil engineering. So in my all research, there is one, I think so, it was DDIC, yes. DDIC is the only experiment for which my supervisors got a postdoc, and he conducted experiments for me. And that his name was, I forgot his name. I can, because he has left UWA. Yeah, Igor Shufrin was the one who actually helped me to conduct the experiment. So he just conducted the experiments. It took him 3 months to get the experiments done, and he just provided me the images. Once I got the images, then I forgot about him, and I just do it. So there is no requirement to understand the geology or something. The only thing you need to understand is that there are two images and you are trying to find the deformation in it. That's all. There's nothing special in it. The only limitation in computer vision, normally our techniques are looking for pixel-wise accuracy, like 1 pixel accuracy is fine. Yes, in those natural problems like geology and all those, we are looking for, or medical images, we are looking for sub-pixel accuracy, like we do not want to make any error in it. So we are looking normally for, ideal is 1/100th of a pixel.
Okay.
I hope I answered this.
Okay. Yeah. Okay. Thank you for your answer. Okay. Maybe any other question from the participant? Okay. 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 I think yeah. If we still not have question from the participant, maybe I can add several question again if you allow it.
Sure.
Okay.
Yeah, sure,
Yeah.
sure.
I think in the first slides, I see that this this methodology can also be used for detecting cancer and so on. Okay.
Yes.
So, but however, yeah, because your field is in the in this subject, but I believe can you give us some of the insight how this algorithm can be applied to detect like cancer or maybe for the medical science, because I believe some of our students are also interested in bioinformatics and also the image processing.
Look, again, as I mentioned, for the case of the engineering, I was not interested in engineering. I was interested in actually deformation management, and I just needed 2 images. That's all. Now, if you look at the medical sciences, what happens is that we have MRI scans, and MRI scans are basically just slices of images. So what happens is that once we get, actually, let's suppose a patient comes in, we have a MRI scan, and we found it out that the patient has a tumor or something like that. Now, what happens is that after 2 months, we want to see what is the growth in the tumor. So we have another set of experiment, or we have another MRI scan. We take these slices and we see what is happening. Now, right now, what happens is that if there is a small change, the problem is that the experts, they cannot actually, with their simple looking with the eye, they cannot figure it out how much it has been changed. Because tumors, the major problem is that tumors grow. And it is right. Also, if you have some medications or laser treatments, then they can shrink. So you need to find the deformation. Our story starts, like, again, I have got actually worked with the Harvard also. I have nothing to do with the medical. What happened is that I get those MRI scans, and MRI scans has got the images. As soon as I get the images, I then use my deformation techniques to actually deformation measurement techniques to find it out. Yes, why do we need DDIC maybe in those cases? Because sometimes what happens is that tumor actually, it not even grows, it spreads or something like that. We want to see what it is, especially if the tumor starts rupturing or something, that is very, very serious. And sometimes the rupture is so small that it is difficult to actually figure it out by just looking at it. And if it is too late, the problem is that it is nearly impossible. So that's why the tumor growth is one of this. Otherwise, as I mentioned to you, when our surgeries are conducted, and especially like brain surgery, because I'm more related to that, when they open, what happens is that there are tissues around the human body which deforms, because this is the reaction that actually the space has been overrun, so they try to. Now, most of the cancerous surgeries, what happens is that they have a laser treatment, and tissues have changed their position, and tissues are deformed. And if they are not precise, we can actually hit the brain or something like that. Because if obviously we are removing the tumor, the tissues have been changed, laser accuracy has been compromised. And if we hit a small, you can say a small leak of radiation to the brain, that like it is very common in the brain surgeries that people have the problem with the reflexes. One of the common, like one of my friend, he had a brain tumor. So when his brain tumor was removed and using the problem was that when he will smile, he will try to smile in brain, his neurons are disconnected, and he will start blinking his eyes. And he could not blink his eyes because the neurons have been disconnected. So that's why it is very important that the high precision is important. And again, it is not that it solves all the problems, it is make sure that actually these problems have been reduced significantly. So that's why medical sciences, again, when we come up, most of the time we cannot work on the medical sciences because we do not have the permission to deal with the patients. We cannot collect the data, all those things. But again, this is where the collaboration comes in. We have a partner from the medical school. We have a partner. I have got collaboration with medical physics, where I am supervising 4 PhD students. The problem is there. We are trying to use how we can use the artificial intelligence or image processing or any other thing to actually solve their problems. Because now, again, all the MRI scans, everything is digitized. I hope I answered your question.
Okay, yeah, thank you. Yeah, it's very clear. Okay, maybe for any other participant who are willing to ask the question. Okay, yeah, we have some. Okay, Shaina again. Yeah, please. Okay.
Yeah. Hi. Sorry. Is it okay for me to ask again?
Yeah, it's
Yeah,
yeah.
sure,
Okay, it's good.
Okay, sure. Yeah, thank you. Actually, regarding the one that Pak Munif or Mr. Munif mentioned just now regarding the related to the medical stuff. Actually, I wonder that you said that what we need is only 2 images, like the first one and after the decomposition, so that you can notice, well, what are the differences. So I wonder, do you have any like pre-processing needs to be done, or is it like just any 2 pictures and then you can just like know where the decomposition, or like you need some maybe image process pre-processing, or like do you have any some rules like the image must be exactly the same like location, maybe like
Yep.
that. Thank
Like
you.
location is something which we are looking at. Good question. Location is something. So we need actually an alignment. Like let's suppose if I'm looking at an image which has a, like suppose stomach or a tumor. So I want the other image to also have the tumor. If it does not have a tumor, then actually I can never correlate because my process will fail. So we need to make sure that actually if there is some information, that information is also there, right? Now, obviously what happens is that let's suppose if you have a brain scan. So brain, if you have 2 brain scans, they will always have a brain. So that makes life a little bit easy. That's why we can actually figure it out what are the deformations. And then we let DIC to actually get the maximize it. Keep on correlation, and actually we try to keep on correlating with optimizing the variables, and it will try to maximize the correlation. And when we get the maximum correlation, that is the new point of it. So this is the only you can say pre-processing, but the image pre-processing, we do not need anything, because DIC works over the research. We have seen that it doesn't work to have the color images. Pure gray level images works well. So what happened is that we do not need color images because color images becomes more complicated, computationally very expensive, and they do not help us a lot. We have found in the research that actually these gray level images are far much better. So what we do is that we use the gray level images, and you know, in medical images, everything is gray.
Yeah.
So that makes actually very optimal scenario where we can use actually these techniques, because they are all gray and we have to figure it out what the gray is happening and all those things. Yes, so structure, what happened is that when we have a structure, we convert the image into the grayscale. It is very easy, or you can buy a black and white grayscale camera, like those black and white cameras, which are very cheaper actually, to be honest. Nowadays, it is difficult to find them because they are so rare. But what happened is that you can just buy them, and that, yes, you need to have a good camera. And if you are looking into the mines, so what we do is that we fix the camera at one position. So if the wall is moving or something, camera is not moving. And that is actually giving us the idea that, okay, yeah, this wall has been moved. But we have to make sure that the camera position remains the same. If it changes, then again, this is the problem, because we do not know, is it the change in camera or the images?
Object.
So, yeah, so that really helps. That is only one pre-processing, that alignment we have to look into it. But otherwise, pretty much nothing special we have to do with the images. Just convert them to gray level, and it is very, very easy using Python libraries or MATLAB libraries. I hope I answered your question.
Sure. Yeah, thank you so much, Professor.
Welcome.
Okay, thank you. Yeah, maybe any other participant who are willing to ask some question? Okay. Okay.
So any of you who have got any questions later on, feel free to actually send me an email. I think I did not write it. So I can actually type it on chat and you can email me if later on you have got any questions. So feel free to send me an email and I'll happy to respond to you guys. So I have shared my email. You can share with the students.
Okay, thank you, Professor. Okay.
So if no questions, then we can conclude.
I think we can conclude our session for this morning. Okay, please go on.
Thank you very
Professor
much.
Basar.
I highly appreciate it, everyone, for their participation and hosting me. Thanks a lot, Munif. Thanks a lot, Ari, and all the participants and who attended my seminar. Thank you.
Okay. Yeah, okay. Thank you. Thank you again, Professor Basar, for your participation. Yeah. Okay, maybe
Thank
thank you also for the participant that's already joined for today's session. Yeah, I think that's all for our today's guest lecture from Professor Ghulam Mubashar Hasan. Yeah, thank you for your great lecture. Hopefully we can see you again in the next occasion, I think. Okay.
Sure.
Thank
It
you
will
very
be my
much
pleasure.
for everyone. I think I will close this session and I will turn